So today we reach lecture 15. And before I start with what we are planning to start for today, actually today we will start with a new chapter. But before that, I just want to review everything we have done so far. So in the very first two chapters, we discussed crystal structures of solids. We focused on these structures that have a simple cubic structures. And why so? Because these are easy to do math on, okay? If we were to take the other ones like triclinic, where we have different angles, we have different sides, then the math will become so difficult, and this is not so important for us at this level in our course. So we focused on the case of like simple cubic, body-centered cubic, face-centered cubic. We learned how to describe a structure by its lattice constants, lattice vectors, by the bases. We took cases where we have only one basis atoms, where we have two bases structures like sodium chloride, or what else? We discussed the case of cesium chloride. Okay, zinc blend, like in the homework. Then in the second structure, we learn how we can find the crystal structure. And we find that we can find the crystal structure by one way is by X-ray diffraction, where we do the diffraction, we find the reciprocal lattice, and from the reciprocal lattice, because we know how to transfer between reciprocal lattice and direct lattice, we can find what is our direct lattice. Then we jump to chapter 4, where we mention that okay, we were assuming in the beginning that the atoms do not move, that they are fixed, okay? And that's how we can find the crystal structure. But in reality, these atoms are not fixed. They are vibrating at a very, 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 very low speed. It's not like they are vibrating at a very high magnitude. No, they're vibrating at a very low speed, and that's because the temperature is not zero. So the crystal will be fixed if the temperature is actually zero. But if the temperature is not zero, it's low enough, we will see that the atoms will start vibrating, and nearby atoms will start affecting the motion of the atoms. Okay. In this lesson, in this chapter, we will discuss thermal properties of solids. That is, when they start, how they are affected by temperature. We will not only talk about very low temperatures, we will talk about any temperatures, okay? So let's start with an introduction. So the story of condensed matter physics, the whole thing will be based on what Albert Einstein and what Peter Debye found about the specific heat of solids. So the story of condensed matter physics starts around the turn of the last century. It was well known that the heat capacity, so at that time, it was well known that the heat capacity of a monoatomic gas, that is a gas made of only one atom, like hydrogen, whatever, CV is equal to 3/2 kb, where this kb is a constant. It was called the Boltzmann constant, okay? It had also been known that for many solids, the heat capacity is given by the law of Dulong-Petit. So it was that the C is a 3 kb, okay? This is different than here, which is CV is a 3/2 kb. The law of Dulong-Petit say that the C per atom is a 3 kb, where C per mole is a 3R, and we know what is the R. Now, here we can look at several materials. So we can find that aluminum, it's 2.91, antimony, 3.03, copper, 2.94. And this law, it seemed to be acceptable for most atoms. This law seems to hold well at room temperature for most atoms, although at lower temperatures, all materials start to deviate from this law, okay? So this law, which is the law of Dulong-Petit, is very fine at room temperature, because I would assume that he did all his measurements at room temperature, but at very low temperature, all materials start to deviate. Now, so let's just give a brief, again, introduction and what we are going to discuss. So in 1896, Boltzmann constructed a classical model that accounted for this law. In 1907, Einstein introduced quantum mechanical ideas to solve the problem at low temperatures, okay? So Boltzmann, all what he did was at high temperatures or room temperatures. So Boltzmann did his measurements at room temperatures, and he found that most of the atoms obey his model, but at low temperatures, they don't obey the model. So Einstein came in 1907 and he introduced quantum mechanical ideas to solve the problem at low temperatures. Now, Einstein's theory of specific heat was successful, but still there were clear deviations from experimental data. So he had a model. Model means like he could solve it theoretically, okay? Like he found equations and they could be solved theoretically, but he also did experimental experiments. He did also the experiments. And when he compared these two, he found there were clear deviations. His model could not explain the fact that at low temperatures, most materials have a heat capacity that's proportional to T cubed. Okay, so remember that in Boltzmann case, it was Kb over 2. In the case of 3 kb over 2, in the case of belong to T, it was a 3 kb. Okay, now in Einstein, we will see together what is his model. But in reality, at low temperatures, most materials, the heat capacity was proportional to T cubed. So that's where Einstein model did not work. Then in 1912, Peter Debye discovered how to better treat the quantum mechanics of oscillations of atoms and managed to explain the T cube specific heat. What we are going to discuss now in this lecture is thermal energy and lattice vibrations, and then we will focus on Einstein model and we will leave the Debye model to another lecture. Okay. So thermal energy and lattice vibrations. Atoms vibrate about their equilibrium position, producing vibrational waves. This is what we discussed last time. In a solid, the energy associated with this vibration is called thermal energy, whose concept is fundamental to understand many of the basic properties of solids. The energy due to lattice vibration. So when the lattice atoms start vibrating, they cause energy, okay? And this energy is called thermal energy. The energy due to lattice vibration is the dominant contribution to the heat capacity in most solids. And this is what we are interested in, to find this heat capacity. We note that the difference between heat capacities at constant pressure and constant volume is Cp, which is the heat capacity at constant pressure, minus Cv, which is the heat capacity at constant volume, is 9 alpha square BVT, where alpha is called the temperature coefficient of the linear expansion, V is the volume, B is the bulk modulus. The fractional difference between Cp and Cv, which is 9 alpha square BVT, is usually small in solids and often may be neglected. That is, people would just say Cp equal to Cv. Now, energy levels of atoms vibrating at single frequency omega are quantized. We took this actually in high school, and they're given by energy levels are n plus half h bar omega, where n can be 0, 1, 2, 3. That is, I can have half h bar omega over 2, h bar omega 3, h bar omega over 2, 3h bar omega over 2, 5h bar omega over 2, 7h bar omega over 2, etc. And a phonon is a quantum of lattice vibrations with an energy E phonon equal h bar omega. So what is, if I give, this is like, let's assume this is my solid. Its energy bands are h bar omega over 2, 3 over 2 h bar omega, 5 over 2 h bar omega, etc. If I show a light, for example, with energy h bar omega, a phonon will be absorbed, it will jump to a higher level, and then it will go back where light will emerge, and this is called creation of a phonon. How did Einstein base his model? He starts by saying each atom in the lattice is an independent 3D quantum harmonic oscillator. So this is the first thing he based his model on. And the second thing is saying that all atoms oscillate with the same frequency. And this is which is different from the Debye model, which we will see in future lectures. Okay, so these are the two things that Einstein based his model on, that each atom in the lattice is an independent 3D quantum harmonic oscillator, and that all atoms oscillate with the same frequency. Now, what we're gonna do is doing lots of math actually. What is the definition of heat capacity in 1 and 3 dimensions? The aim of this section is to find the heat capacity. T is del average value of E by del T, or expectation value of E by del T. T here is the temperature. And discuss the high and low temperatures limits. So we will find del E by del T, and then we will discuss the high temperature limit and the low temperature limit, and we will assume that in between we can draw it by eye. Okay, so we need first to find the expectation value of the energy, which is this thing over here. This is the expectation value of energy using the partition function Z. In 1 dimension, the eigenstate of a single harmonic oscillator En is h bar omega n plus half, where omega is the frequency of the harmonic oscillator. So remember that we will be dealing as if each atom is a independent harmonic oscillator with common frequency. So we will say that omega is fixed for all atoms. Sometimes this frequency is quoted as Einstein temperature, which is h bar omega is kB TE. Okay, that is kB times the temperature, Einstein temperature. So let's start. So what is the partition function Z? The partition function Z in 1 dimension is summation of e to the minus beta En. The expectation of energy is summation of P and En, where Pn, this Pn is the probability of an oscillator. It is 1 over Z e to the minus beta En. Okay, so now we have that absolute expectation value of E is minus 1 over Z del Z by del beta, which is minus del n Z by del beta. We're gonna show this. So we start by Z is summation of e to the minus beta En. Del Z by del beta is what? The minus En will jump outside, so it is summation over n minus En e to the minus En. What is 1 over Z del Z by del beta? It is 1 over Z En e to the minus beta En, implies expectation value of E is minus 1 over Z del Z by del beta. Okay. So this by, you see it by, so this is here, expectation value of E, where P is 1 over Z e to the minus beta E Z. Now, look, what did we find here? We found that minus 1 over Z del Z by del beta is the summation of 1 over Z e to the minus beta En, which is this thing over here, times En. So this is nothing but the summation over N, P, N, En. So indeed, the expectation value of E is minus del n Z by del beta. So now, again, what is Z? Now we will, from Z, we will find what is len Z, and then we will do del len Z by del beta, and by that we find what is the expectation value of E. So let's start. Z is summation of e to the minus beta En. It's here by definition. This is equal to summation e to the minus beta h bar omega n plus half. Remember that En is h bar omega n plus half. What is this? If n is 0, this is e to the minus half beta h omega. If n is 1, this is e to the minus 3 over 2 beta h bar omega. If n is 5, this is e to the minus 5 over 2, etc. And this is equal to what? If I take common e to the minus half beta h bar omega, I will have 1 plus e to the minus beta h bar omega plus e to the minus 2 beta h bar omega, etc. Now, what is 1 plus e to the minus? What is this thing? This thing is 1 over 1 minus e to the minus beta h bar omega. This is a geometric series with the first term a equal 1 and common ratio r e to the minus beta h bar omega that converges to 1 over 1 minus r, which is in this case, so this is my r, okay? Sorry. This is my r over here. Okay, so this converges to 1 over 1 minus e to the minus beta h bar omega. So now I have z is equal to, so this is equal to, first we found that it is equal to the summation of e to the minus beta h bar omega n plus half. Now we know that it is equal to this term, which is e to the minus half beta h bar omega, okay, divided by 1 minus e to the minus beta h bar omega, because this term over here, which is underlined, is nothing but 1 over 1 minus e minus beta h bar omega. Okay, so this term is here and this term is this term. Now let's take the logarithmic value of this thing. It will give me the logarithmic value of the numerator minus the logarithmic, the ln of the denominator. So I will have ln e to the minus beta h bar omega over 2 minus ln 1 minus e to the minus beta h bar omega. Ln exponential cancel each other, so we'll get minus beta h bar omega over 2 minus ln 1 minus e to the minus beta h bar omega. And this is ln z. Now, what is the expectation value of E? It is del ln Z by del beta. So I will take the derivative of the first term by beta, and I will get h bar omega over 2. And then I will take the derivative of the second term by del beta, and I will get h bar omega e to the minus beta h bar omega over 1 minus e to the minus beta h bar omega. Okay. And this is equal to, I will take h bar omega as a common factor. I will get 1 over 2 plus e to the minus beta h bar omega over the denominator. And this is equal h bar omega into half plus, I will multiply up and down by e to the beta h bar omega. So I will get 1 up and down, I will get e to the beta h bar omega minus 1, implies expectation value of E is h bar omega into half. So the half is here, this half is here, plus this function NB of beta h bar omega, where NB of x is 1 over e to the x minus 1. So we found the expectation value of E. Now, let's take, so now that's the expectation value of E. What is the heat capacity? The heat capacity, we agreed that it is the derivative of the heat, of the energy of the expectation value of E by del T. So it is the derivative by del T of h bar omega half plus 1 over e to the h bar omega over kBT minus 1, where beta is kBT. Okay, so I put instead of beta its value. Finally, C is equal to, so I will take the derivative of this thing by T. So I will get this value for C, which is KB into beta h bar omega square e to the beta h bar omega over e to the beta h bar omega minus 1 square. So you just have to take the derivative by T of this thing, okay? And you will do it. So do it just slowly. Now this is in 1 dimension. What happens in 3 dimensions? In 3 dimensions, our energy will be h bar omega into an x plus half plus an y plus half plus an z plus half. Now, if I do this partition function Z, I will get that it will be in 3 dimension. It is nothing but Z1D in times to the power 3, okay? Because it is summation E minus beta E and X, summation E minus B beta E and Y, summation E minus beta E and Z. So it is the multiplication of the 3 together, resulting in the expectation of E3D is a 3 times the expectation value of 1D. So C is 3 KB beta H bar omega square E to the beta H bar omega over E to the beta H bar omega minus 1 square. And remember here that beta is 1 over KBT. So now, remember, we will be interested in looking at high temperature. So just by this, but this one to draw, I need like a computer. So I will use Mathematica or MATLAB or any or C++, and I will put what is the value of KB. Beta is 1 over KBT. So KB is a constant. T will be my variable. H bar is constant. Omega here is also constant. It depends on each atom. Each atom has a different frequency, but it's a constant term. Everything else is constant. And if I draw this thing like using MATLAB, Mathematica, or anything, it will look something like this. This is how it will look. Okay. So this is in terms of KBT over H bar omega. This is how C will look like. But we are interested at looking at particular values, which one at very high temperatures. High temperatures means KBT is much bigger than H bar omega. Okay, so that is beta H bar omega will be very small, this value over here. It will be very small. So what is E, or this term over here and this term over here? Okay, so what is E to the X? E to the X is 1 plus X over 1 factorial plus X squared over 2 factorial plus X cubed over 3 factorial, etc. For very small value of X, E to the beta H bar omega, this form of this thing over here, can be only 1. Okay, I will only take for that the first term. Okay, and E to the beta H bar omega minus 1, I can choose to be 1 plus X over 1, 1 plus X over 1, so 1 plus beta H bar omega. Okay, why didn't I take only one term? Because if I take only beta H bar omega equal to 1, I will have 1 minus 1, and this will give me infinity down. So I don't want 0 denominator. That's why I will take the first 2 terms. So for beta H bar omega in the numerator, I will only take the first term. For beta H bar omega in the denominator, I will take the first 2 terms. So 1 plus beta H bar omega minus 1. So I will have beta H bar omega. Okay. And I will find that my C now will be 3 KB beta H bar omega squared times 1. So in the numerator, I put 1, and down I will put E to the beta H bar omega squared. And finally, beta H bar omega squared and beta H bar omega squared cancel out, and I will get C goes to 3 KB. And this is the same result as the law of Dulong-Petit. Remember what is the law of Dulong-Petit up there? Let me show you. The law of Dulong-Petit is that C is 3 KB. So this is true at room temperature. So what Einstein did is true at low temperature. So at room temperature. So here at high temperatures, okay, notice that it is a straight line. It is constant, sorry. It is constant. C over 3 KB is constant. Now, what happens at low temperatures? So at low temperatures, we go back here. This is my C at any temperature. It's a 3 KB beta H bar omega squared E to the beta H bar omega over E to the beta H bar omega minus 1, all of it squared. So what happens at low temperatures? That is when beta H bar omega much bigger than 1. the degrees of freedom freeze out, the system gets stuck in only the ground state, which is the eigenstate, and the heat capacity vanishes rapidly. So here, if I put beta h bar omega is much, much bigger than 1. So if I do here the expansion, what is e to the beta h bar omega minus 1 squared? It is e to the 2 beta h bar omega plus 1 minus 2 e to the beta h bar omega. And now if e to the beta h bar omega is much, much bigger than 1, the only term that will stay will be the e to the 2 beta h bar omega. So I will get 3 kb beta h bar omega squared, e to the b beta h bar omega over e to the 2 beta h bar omega. And this will give me 3 kb beta h bar omega squared over e to the beta h bar omega. This thing goes to 0 because here I have an exponential of something which is very big. So this thing goes to 0. And what you see here is this is what's happening here. At very, very low temperatures, C is almost 0. At very, very high temperatures, C is constant. C over 3 kb is constant as a function of T. Okay, in between we have a figure like this, which we can only draw, which is difficult to draw by hand. We use a computer or a model to draw it. Now, Einstein's theory explained the behavior of the heat capacity as a function of temperature with only a single fitting parameter, the Einstein frequency omega. But this theory fails to explain the dependence in T cube of the heat capacity at low temperatures. So he did all his measurements by taking that the omega is fixed, but in reality, there is also dependence on the temperature, and it's a T cube dependence. And this is what is not found in his calculations. There is no T cube dependence. And this is what Debye will show in future lectures. Now, the heat capacity of diamond, for most materials, the Einstein frequency omega is low, okay? For most materials, the Einstein frequency is low, which satisfies that beta h bar omega is much, much less than 1. And thus, the Dulong-Petit law holds fairly well, okay? So the Dulong-Petit law holds, the Einstein holds at high temperatures, okay, where we found that it is constant. However, for diamond, omega is very high, which does not satisfy h bar omega is very low, is much less than kBt, and so the heat capacity is lower than 3R at room temperature. Room temperature is very low for diamond. So when the temperature is raised, the heat capacity increases towards 3R. The reason diamond has such a high Einstein frequency is that the bonding between atoms in diamond is very, very strong, okay? When the bonding between atoms is very, very strong, the frequency of oscillation will be very high, okay? Because think of it this way, like you have two masses connected by a spring, and this spring constant is very, very strong, okay? So if the two atoms oscillate, they will oscillate, the period of oscillation will be very, very low. So the frequency of oscillations will be very, very high, okay? Especially also that the mass of diamond is also low. So omega, which is a square root of C over M, oscillation frequency with C, a spring constant, and mass M. So this is why diamond does not follow. So we can say that the Einstein model or the Dulong-Petit model are acceptable, but they are acceptable for most materials because their frequency is very low. But in the case of diamond, for example, it is not acceptable. This is why more physics need to be done, and this is done by Debye, where we will see in section 3. This is the end of today's lecture, and if you have any questions, just send me an email. Bye-bye.